Hello friends, welcome to the Tech Granth. Today we will talk about quick select algorithm. So this algorithm is used in place where we want to find a solution for the problem which says that you need to find the kth smallest element in an array or kth largest element in an array. So you need to do it in place, which means that you don't need to have additional or extra space that you want to add to basically select that element. So let us look at an example and we'll see how quick select will help us in solving this problem in a better way. So if we have suppose an array, this array is something like we have 4, 5, 10, 11, 1, 3, say 19, maybe 8 and 7. Okay. So there are how many? 3, 6, 9 elements in our array. And suppose we want to find the 6th smallest element in this particular array. So 6th smallest element in this particular array will be 8. So that is our answer in this particular scenario. Now how we can approach this particular problem? The simplest or the most trivial solution that will come to our mind is we sort this particular array. So if we sort the array, then the 6th smallest element is equals to the 6th element of the array. Okay, so let us sort this particular array. If we sort the array, we will get an array something like 1, 3, we have 4, we have 5, we have 7, we have 8, and then we have 10, we have 11, we have 19. So the 6th element here is 1, 2, 3, 4, 5, 6, which is 8. So the solution here is, or the answer here will be this element, which is the 6th element, and the answer is 8, which is correct. Now let us look at the time complexity for this particular approach. So the time complexity for this particular approach depends on the type of sorting algorithm that you are using. If you are using quick sort, it will be order of n square. If you are using merge sort, it will be order of n log n. So it will be O of n log n and space will be the space of the array, whatever space the array is taking. All the sorting will happen in place. So this is one of the solution. Second solution is if we are allowed to have an additional space in that particular scenario, we can go for heap, the min heap or a max heap, or in if you are using Java, you can use priority queue, so you can use PQ. And as part of the PQ, or in case of min heap implementation, what you can do is you can keep on adding element to this particular min heap. So let us do that. If we start from 4, so our heap will look something like this. We have 4 initially. When 5 comes, the heap will have 5. I am putting it in like in order, where if this, you can imagine it as a flat queue with the tail, or basically the head towards the right hand side. So we have 4, we have 5. The next element that comes is 10, so 10 will be placed here. Then 11, so 11 will be placed here. Then we have 1, so 1 will be placed here in the priority queue. Then we have 3, so 3 will come here. We have 19, so 19 will come in the end. And finally we have 8 and 7. So first 8 comes, so 8 will be here, and then 7 comes, so 7 will be here. So this is how our priority queue will look like. Now we can start popping out or removing element from the priority queue till we hit the 6th largest element, or the 6th smallest element. So we'll start pulling this particular queue. We'll remove 1, so that will be count 1. Then we'll remove this 2, then 3, 4, 5, and finally when we remove the 6th element, we can return the 6th element, which is our answer. So in this particular scenario, we have our solution, which takes a space complexity of O of n. This is space, because we are using this priority queue, which will take n elements, which is whatever is the length of the array. And for time, every time we insert an element, it takes log of n. So for populating the complete array, so time, if we see, for each element it is O of n, O of log n, sorry, and this will be done for all the elements, so this will be n log n. This is the time complexity. And finally we will basically pop from this priority queue also. So popping is in constant time, so we are good there, but we'll pop for n elements, so overall it will be this plus n. So finally, if we basically, this will be O of n plus n, and this will be O of n log n in the complexity analysis. So time wise it will be O of n log n, and space wise it will be O of n. Now the question comes, can we do better? So yes, in general scenario we can do better than this, and that is where the quick sort algorithm comes into picture. So not quick sort, quick select. So quick select is nothing but an implementation of quick sort. But what we do as part of quick select, let me just copy this particular array here. So when we do quick sort, what we do is we create a pivot point and then sort the element across the pivot. So here, if we take an example of quick sort here, if I want to run quick sort in this particular example, so what we can do is we can create a pivot right here at the last element, and then we basically sort this particular array. So for that, what we need to do is we have to basically sort the array based on this pivot 7, so that everything on the left hand side of 7 is smaller than 7 and everything on the right hand side of the 7 is greater than 7. So for the first time when we basically sort this particular array across the pivot value, so the pivot will come to its particular place where it should exist in the array. So if we look at the solution here, after we sort it for the first time across the pivot 7, our array will look something like this. We will have 4, 5, then we will have 1, 3, then we will have 7, and finally we will have 10, 11, 19, and 8. So 7 has reached its correct place because everything on the left hand side of 7 is smaller than 7. Everything on the right of the 7 is greater than 7. So it means that 7 has reached the point in the array where it should be. Now the trick here with quick select is, if 7 has reached its correct point and if that point is the kth point, then that is my answer. I hope the explanation is clear. So let me tell it again. If 7 has reached its correct position in the array, and if the position where 7 has been placed is the kth position, so in this particular solution we are looking to find the sixth smallest element. Now after we made 7 as pivot, 7 has reached some point. Now this point is the fifth position in the array. So if suppose we were looking for the fifth smallest element in the array and 7 has reached the fifth position, it means 7 is the fifth smallest element in the array. But in our case it is not happening because we want the sixth element. But our pivot location, now the pivot that we have got is the position 5. So here we have got position 5. Now this position or this pivot position is less than the kth solution that we are looking for. We are looking for sixth smallest element. We have found the fifth smallest element. What it means is that the sixth smallest element is not there on the left hand side of this particular array. It will not exist here. Why it will not exist here? Because everything on the left of 7 is smaller than 7. So we need to look for the sixth smallest element in the array on the right hand side. So we'll look for the solution. So our solution is somewhere here. Now next what we need to do is we need to follow the same approach, and we need to find the basically we need to find where is the sixth smallest element. So for this what we need to do is we need to sort the array on the right of the 7. We don't need to touch anything on the left hand side. So left hand side will remain something like this. It will still be 3 and it will still be 7. And now we need to play around with what we have here, which is 10, 11, 19 and 8. So next we will create a pivot around this number 8 here, and we will not even consider this part of the array. We will only consider this part. So we need to move the element 8 from this position to this particular position. So the movement will be between these two places. So let us look how the array will look in the next approach or in the next iteration. So when we have found the pivot, now pivot is at point 8, 4, 5, 1, 3 and 7 will not be touched. And now what we need to do is we need to put every element which is smaller than 8 between this point which is 10 and between the pivot on the left of 8 and everything which is greater than 8 on the right of 8. So in this situation what it comes out that 8 will be the smallest element, so 8 will be on the left part and everything else will go on the right hand side. So this will be 11, then 19. Now when I look at this particular this particular array, 8 has reached some point and everything on the left of 8 is smaller than 8, everything on the right of 8 is greater than 8. What is the position of 8 now? The position of 8 is 6th position. What is the value of k for us? This is the kth position for us. So what this means is that we have found the kth smallest element in this particular array, which is the 6th smallest element in this particular array. So if we see, we are leveraging the quick sort to find the kth smallest element in this particular array. And why this is better than quick sort? So quick sort, if you see, it takes order of n square, but quick select in general case it will be order of n. The reason being, if the array is something like this, you will get it in a matter of the number of iteration, which is equals to the number of your element. But if suppose there is a case where your array is sorted in descending order and you have to find the the kth element is basically is equals to the size of your array. So you are basically pivoting towards the very end, which is the smallest element in this particular array. The largest element is lying somewhere here. So in that particular scenario, it will go up to order of n square, but in general case, this will be an order of n solution and the space will be constant because you are doing it in space or in the array which you have been given. You are not using any additional space. So this is the approach that we are going to take, and next we will jump into the code editor and we will basically solve this problem and we will write the algorithm to do quick select. Let us look at the implementation of quick select. So what we need to do is we will create a method called get kth smallest element, and here we need to pass our array and 6, since we want the 6 smallest element. So let us create this particular method and we want to return int from here, and let us print that also. So we'll print saying that the 6 smallest element is this plus whatever we get from here. Okay, so for getting the 6 smallest element, what we need to get is we need to get our pivot point, like we have discussed in the previous section. So we need the pivot point, and to get the pivot point we'll create another method which says that get the pivot point for me. And what get pivot point will require is it will require the array, it will require a lower bound, and it will require a higher bound between which it has to traverse. So the pivot point in initial case, so suppose if we make the pivot element as 7 and this is our first iteration, so we need to basically look at the complete array which is from 4 till the 7 to find what is the correct location for 7. But suppose after first iteration, if 7 has reached at some particular position which is its correct position, then what we need to do is we need to look either on the left hand side or the right hand side, which will be the location of next pivot element. So we don't need to search the whole array in this case because we are not sorting the complete array. We are just finding the sorting the array till the kth element has reached its particular point. So that is why we require a low and high bound. We'll pass it here itself. We'll say this is as k. We want low, we want high, and here we say that when we start, our lower bound is 0, our higher bound is whatever is the array of length minus 1. It will be the higher bound of the array. We'll create this, but we'll implement it later. Once we have the pivot point, what we need to do is, if the pivot point that we have got is equal to k minus 1, because it is 0 based indexing, so the kth element will actually be the k minus 1th element in the array since it starts from 0. So here we will simply return the array and whatever is the pivot point. That is one thing. Otherwise, if it happens that the pivot point that we have got is less than the kth position, which was our case. So if you remember, or you can go back in this particular video and see, in the tutorial I told that after first iteration this array will look something like this. We have 4, we have 5, we have 1, 3, 7, we have 11, 19, 8. So did I miss anything? I missed 10. So it looks something like this. Now the pivot point that I got from first iteration was 5, which is less than 6. Our target, or the 6, we are looking for 6 smallest element. So we know that till 5, this is the 7th, 7 is the 5th element. So everything before this is less than the 6th smallest element that we are looking for. So our 6th smallest element will be on the right hand side. So if the pivot point, in this case the pivot point was 5, where we got the value 7, is less than the 6th element, so we need to look on the right hand side of the array. So what we will do here is we need to basically get the element, or the get smallest, kth smallest element from the same array. Now the low, or the starting point of the array will be whatever the current pivot point that we got plus 1 till the high. This will be the logic to get the kth smallest element if the pivot point is less than the 6th element or the kth element we are looking for. Otherwise, it means that the pivot point is on the higher side and the point we are looking for is on the lower side, which is on left hand side. So suppose here the pivot point we got was 5, and we are looking for second largest or second smallest element in this particular array. So it means that the second smallest element will lie on the left hand side. So in this case, what we will do is we will return, you get the kth smallest element from the array. The starting point will be low, and highest point, or the upper bound of the array till where we have to look is, it will be till pivot point -1, because we know the pivot point, that is the k plus 1th smallest element in this particular element, in this particular example. So this is what kth smallest element will do for me, and finally it will return me the correct answer. Now the only thing left is how to get the pivot point for me. So we saw in the example that for getting the pivot point we require a pivot element. So we took the highest element, as in this example, whatever is on the rightmost side as the pivot element. So we'll take int one pivot element. So this pivot element will be equal to, in my array, whatever is on the highest location. Now we require a pivot point. So how we will determine the pivot point is, we start from this location, or the leftmost location, and we'll see whether we need to keep that element on the left of the pivot element or on the right of the pivot element. So we have the pivot point, and this will start at the lower index, and in the end we need to return this pivot point only. So this is how we will get the pivot point. So we have the lower bound and we have the pivot element. Now what we will do is we will check against each element whether it is greater than or smaller than the pivot element. If it is smaller than pivot element, we'll keep it on the left hand side of the pivot element, otherwise we'll keep it on the right hand side of the pivot element. So for that we will require a loop. We'll say you start from the lower bound and I will go till the higher bound, and we'll do I plus plus, and we'll see if array of I, if this is less than my pivot element, it means that I need to keep it on the left hand side. So we will take array of I here, and my array of I, this will be equal to my array of pivot point and array of my pivot point. This will become 10. So we are just swapping, so just swap these two. So what we did here is, so let us take an example. So this was our initial array, sorry. sorry for the bad mouse. So we had, this was our initial array. We made the pivot element as 7. We started from 4 here. So we need to loop from 4 till the end, and here we will see that if 4 is less than 7, what we need is we need to swap it with the pivot point. So we started the pivot point here itself. So we have pivot point, this is say we are using 1 based indexing, but actually Java will use 0 based indexing. Just for explanation, I am using 1 based indexing here, and the value of I is also equal to 1. So what we do is basically we are just swapping these two elements, and 4 will be in its own position. Next, when the I is equals to 2, so and pivot, we need to basically here, once we have swapped, what we need to do is we need to increment the pivot point so that we go to the next element. So pivot point will also become 2 here. Now 5 is less than 7 again, yes, so we will swap these. So pivot point will become 3. When I becomes 3, in this particular scenario we have 10. So 10 is not less than 7, will not do anything. I will become 4. When I becomes 4, we have 11 here. 11 is greater than 7, will not do anything. I becomes 5. When I becomes 5, we are at 1. So what we need to do is we need to swap with the pivot element. So array of I and pivot element will be swapped. So what we will do is now this array will look something like this. It will have 4, 5 and 10 will be swapped with, which is our pivot point element 10. It will be swapped with the ith element, which is 1. So this will be 1, 11, 10, and then it will be 3, 19, 8 and 7. Okay, and now my pivot element will become 4. Next time when I go, I becomes 5. When I becomes 5, I have the, in this particular case, when I becomes 5, I am here at number 3. So 3 is again smaller than 7. So we'll again swap it with the pivot element, which is fourth element, which is this one. So now it will be 4, 5, 1, 3, 10, 11, 19, 8 and 7. So the fourth element is 3 now, and pivot will become 5. So we are here. Now I goes to 6. This is again less than 7, greater than 7, will not do anything, will not do anything, will not do anything. And finally this comes to 7 and will come out of the loop. So we have found the pivot point is 5. This is our pivot point. So once we come out of the loop, what we need to do is we need to move our pivot element to the pivot point. So here what we'll do is we'll again swap. So we'll say in temp is equals to array of the pivot point, my array of pivot, not element, sorry, my array of pivot point will be equal to this will be equal to whatever is on the higher side or whatever we have created as the pivot element. So this will be high, and array of high will be equal to 10. So we have swapped, and finally we'll return our pivot element, pivot point. So this is how the pivot point implementation is done. Let us run this particular code and we'll see the solution should be equal to, in this particular scenario the answer was 8, which is the 6th smallest element in this particular array. So 6th smallest element is 8. So suppose we are looking for the 5th smallest element, which is 7. We'll change it and we'll run the code. Oops, we are looking for 7th, I'm sorry, we want 5th, and this will be 5. Apologies. So the 5th smallest element is 7. So it seems the code is working fine. So you can get this code from the GitHub link. It is posted in the description of this particular video. That is it for this video. Do comment if there is any confusion regarding this. Like the video if you reached till here, and let me know what other algorithm you want me to create a video on. Thank you for watching Tech Granth. Take care. Bye.